I know, I'm amazed how good Zoom is. And the files are small. Zoom is very advanced. Yeah. In what class? Yeah, what about it? What do I mean by it? All right, let's take a look. Challenge 2. Should be able to connect to that server, although probably not on the City College network. Get rid of these things. Okay, there. This is just the same software running on a remote server. You can now take over that server, but in this project, you just had to put your name in that file. So what's your question?
So what do we do inside?
You have to put your name in this file and create that file, and then you'll be on the winners page. It's just that it's running on a remote server.
So I can look at those files?
You can, in fact, look at them, but you don't have to. All you have to do is put your name in them. And every 1 minute, if those files exist, that person is put on the winners board and the files are deleted. There's a cron job run.
No, but the whole file is very long. I don't think there's anything to do.
There are about 40 people on there, huh?
I don't think there's anything.
Well, perhaps something is wrong. Let me see. Here are people that got on it. And here's people that got on it today. So it can be done. So all right, let me take a look. I can go here and I can send, so it's 40 characters.
Oh, it's running the same program?
And then LS. And there, now let's see where we are. Let me get this in the clipboard. Okay, so I connect. Now let's get PWD and then LS minus L. Let's see what that does. Okay, so I'm in home P1X. Okay, there is a file called update now, and there's no file called winners. So I can put myself.
The $IFS, it's a inside variable? Or?
It is an environment variable called the interfield separator. And it's one way to send a space up.
I did another way. Maybe.
There is another way. You can do this. You can just put a quote in and then put in that junk and then put in a space all you want. And it didn't work because I guess I have to move a character. Let's try that again.
You're giving away your answer.
Yeah, that's all right. I'm willing to. There. Now, still did not do the LS minus L. Yeah. So the IFS works. I don't know what quotes worked on some of the others, but maybe not on this one.
Can you make that bigger, Sam?
Yeah.
I did another way.
Yeah. There's a lot of ways. You can also do it with a backslash.
I think that's another way.
There's lots of ways. Yeah.
I went inside change the C program.
What's that?
I went inside change the C program. I did another way.
Inside the C program?
Yeah.
On this server?
No, not in this server.
Oh, yeah. There's if you have your own server, you can modify the code. Yeah. But on this server, you got to exploit the existing code. But that's all. And so you can see nobody has made the winners file there, but you could. If you put your name in the winners file and you create one called update now, it will. Now, another thing that happens sometimes is people create directories that block things, but that did not happen here. There's a file called update now, but they just haven't put their name in the winners. So anyway, I think it's all right. That was one question that came up. So this is 127, and I guess I've got the people that want to attend face-to-face, with not very many, which is all right. I just want to remind you, because I got an email that made it clear that some people are confused. This is not an official City College class. You don't need an ad code. The administration here doesn't know it's running. And if you tell them, they will probably yell at me and make me not stop teaching it because they don't like anything they don't understand. They will presumably add it to the schedule next semester. And then if you want to get credit for what you do this semester, you can tell me and I can give you a grade next semester. But they just, they're sort of nuts around here. So, yeah. No, what's on the board is actually for 123. So forget about that. Good point. Okay. Thank you. Good. So Okay, any questions about anything? Well, let me go on. I've got a couple demos to give you, but let's start with the chapter and then I'll demonstrate the latest projects, which are good, clean fun, of course. So we got a very simple exploit working last time. And now we're up to proper shellcode. So the issue here is, this is what the title of the book's about, making shellcode. Although we're going to use a tool to make most of our shellcode, this is the class where we'll talk about writing your own shellcode to some extent. We're not going into as much detail as the book because there are tools to do it for us now. But here's the topics: protection rings and syscalls are the main thing. And there are some tools to learn, like NASM, the assembler, LD is the linker, obj dump is very important. This is how you look inside files to see what's in there. It's very useful to find sections of code and to disassemble compiled code. And strace is useful to debug crashes. And they're all included in almost every Linux version. You don't really need Kali Linux. Ubuntu would work fine. It's very rare that any Linux version doesn't have all these available because they're used typically to make normal software. So here is the heart of shellcode. And for that matter, really almost all software. If you are in user land, which is in Windows, everything you launch after logging in from the desktop, from the start button, all those things run in what's called user mode. Now, this is a protection model of the processor. So there's a set of assembly language instructions available on the processor, and some of them are considered too dangerous for users. And those are only available to the kernel. And everything that goes directly to the hardware is too dangerous for users. So you are not allowed to directly send anything to the hardware. All you can do is use the API to ask the kernel to please do that on your behalf. And that is why device drivers have to run in the kernel. And that is why bad device drivers cause Windows blue screens of death. Something like 3/4 of all the Windows blue screens of death are caused by non-Microsoft software, which is why Microsoft got an attitude. In each version of Windows, they have more and more elaborate warnings about drivers because people complain to Microsoft and it's not really their fault, and they're kind of fed up with it because people that make cheap hardware just take their driver from something like Windows 95 and keep using it on later versions when it really doesn't work very well. And anyway, that's how it works. So shellcode is the code that you're going to make to a takeover server. So it's going to be translated into hexadecimal opcodes and injected onto a server. And typically what you want to do is make a root shell, which lets you just type in command line commands. That's why they call it shellcode. It could be something else, but that's the most common thing. And the way you do this, you're going to be making syscalls. A syscall calls to kernel, and you can do many things. There are a bunch of kernel functions you can call, and you call them all with interrupts. And this is how you move from user mode, where your code runs, into protected kernel mode, where you have complete access to the computer, where you can do things like directly interface with the hardware. So here's the point. There are protection rings built into the processor itself. There are 4 rings. And only ring 0, the kernel, is actually able to use all the machine language instructions. There are 4 layers, but for some reason, nobody uses layers 1 and 2 at all. It was only used by some old experimental operating systems that never went anywhere. Windows and Linux use only ring 0 and ring 3. Everything in user land is ring 3, the most restricted, and then you jump right to kernel and have total access, and that's it. This does lead to a variety of unpleasant things, such as hypervisors have a problem, and antivirus software has a problem. Antivirus, if you double click on a file on the desktop and you try to run it, the antivirus needs to grab that action before you run the file and scan it. So it has to modify the kernel, which really, really irritates Microsoft, because they would rather have control of the kernel and be able to identify an intact kernel. And if the kernel is modified, they would like to warn you have a rootkit and not start up. But they can't do that if other companies are modifying the kernel. And this really came up with the Meltdown and Spectre exploits. Microsoft tried to patch the kernel routines around them. And it turned out that if you had antivirus, those patches would not work or even cause the blue screen of death, because the antivirus people had to mess with the kernel, and they did not obey Microsoft's best procedures for messing with the kernel. So when Microsoft did an update which met their idea of success, it did not get along with their modifications, and so people fight over the possession of the kernel. But anyway, that's the way it works. And so protected kernel mode is there to prevent applications from compromising the OS. The point of this is if you write an application and you make a mistake and it crashes, it does not kill the machine entirely because the kernel keeps running. So it will just crash and then pop up a box saying your application has crashed. Maybe you should restart it or something. And it doesn't stop all the other processes because you didn't compromise the heart of the OS. That's the idea. Now, if you try to access kernel memory directly from user land, the code will not run and it will generate a access exception. That's how it's prevented. And this is, of course, how Spectre works, which I talked about, I think, at the start. The problem with modern processors, which is not in your book because this only came out a month ago, is that they have pipelining. So they begin executing instructions early. And so if you do try to access kernel memory from user land, it will generate an exception, but that exception will not take place until it has actually executed many more instructions, assuming that was going to be okay. So in fact, several instructions can be executed violating this, and that's the problem with Spectre, which is very difficult to fix. But anyway, aside from that detail, which nobody knew until earlier this year, you are not allowed to do anything, any kernel mode stuff from user land. All you can do is make syscalls. And syscalls call a library routine which will run a kernel thing on your behalf. A libc is how you typically do it from inside C. And this is just a C function, which will then do a syscall for you. All right, this means it is considered poor form to jump directly to the kernel. It's better to use the C library command from inside your C and go through that. That is under more control. It's more likely to be able to handle errors and such. So a professional product will be written in C. It'll use libc to perform the syscalls. But hackers who want to make shellcode want to make it as small and fast as possible, so they remove all the intermediate steps. This also is an important fact about shellcode. Shellcode is designed to be small, so it has no error handling. So if something goes wrong with your shellcode, it will just crash. So if you make a reverse shell that tries to connect to you and the IP address is wrong, it will just crash. It doesn't pop up an error message or anything. This takes some getting used to. It's not like professional code. So syscalls run with int 0x80. And your argument, the first argument goes in EAX. EAX is the register that tells it what you're doing. That's the number, which determines which system call you're making. And the system call may have other arguments, and they go in the other registers. Then you execute int 0x80. You do not move the extended instruction pointer into the kernel. That's what you would not be allowed to do. You perform an interrupt, and the interrupt then requests the processor to please service a kernel routine. That's the mechanism that is used to execute something that you can't jump to directly. Then the CPU switches into kernel mode, executes that, and returns. So there's an integer in EAX, and then you have other arguments that go in the other registers like B, C, and D if you need more arguments. If you have a long list of arguments, it'll just put a pointer in EBX to a data structure that includes all the data. But most of the things we're doing here are very simple. So the simplest shellcode you can make is shellcode that just exits normally. This will accomplish nothing, but it lets us see how the structure works. So here's the entire C code for this thing. And let me bring it up and do it live. I've got show my slides over here and bring up my Kali Linux machine and connect to it over SSH. Okay, so now I'm in. All right, I think I've got all these things ready to look at. Yeah.
Is that equivalent to loading PuTTY, like you said, and then putting the IP address in it?
Yes. The SSH in the command line on the Mac is the same as PuTTY on Windows. And now supposedly they're finally putting SSH in Windows. I think if you get the latest version of PowerShell or something, it's finally in there. Microsoft gradually moves towards Linux as they get over it. Yeah.
I actually was trying to do it with the Windows 10 machine, and I couldn't do it through their integrated. So I downloaded Putty and then got to experiment with it. But I was trying to follow along with your one of your other things. I think one of your other courses is difficult.
Yeah, Putty has been the way we've done it since like the days of DOS, and it works. It's been the standard. Because Microsoft has never gotten on board with SSH until recently. They had their own RDP, which just doesn't replace SSH, and they're finally knocking it off. Anyway, so if I go into 127, this code, whoops, this code should be there. Okay. And it's called it's called e.c or exit.c. I think I called exit.c. Okay, so exit.c looks like that. That's it. Just one command, exit 0. So it's going to use the C library routine to do the syscall to exit. So I can compile it, gcc minus static. So it will put everything in one file instead of referring to shared libraries that are going to be hard for me to see in the debugger. And then put the output in exit and put it in the input exit.c. Now, you get warnings. I had students emailing me saying I can't use GCC, it crashes. Warnings are normal. You're going to see a lot of warnings because the whole point of this class is we're making vulnerable code that makes mistakes that you shouldn't be making. And so GCC will warn you. But if you don't see an error, it still produced the output file and you can still use it. This is what it does. So it's normal that you see warnings, and with every version of GCC, you'll see more warnings, but it runs. So now there's a program called exit. If I do this, I can see I now have an exit executable file, which I just created, 1:16 p.m. So that's it right there. Notice it's 637 kilobytes big. That is the object code that does it. My source code, of course, is down here. It's only 21 bytes big because it's only 1 or 2 lines of code. So now, if I run this, it just comes back exiting normally. So that's not very exciting, but that's what it does. This is just how we get started. Now, to see what it does, we're going to disassemble it. So gdb./exit. Okay, now I'm in GDB, and I can now disassemble main, which is the name. That was a name I typed in the routine, and every C routine typically has a main in it. So here's the code for main, and let me make this bigger. Okay, so this is the entire code for main. So what it does, this is the prologue preparing the stack. It's rounding off the stack to an integral multiple of 16 bytes, then pushing things on the stack to prepare for local processing. Then it's going to call this thing that does thunk, which I think is more preparing the stack. Then it's finally going to put things on the stack. It's going to call exit down here. This is calling a system routine to do exit. So the main calls something called exit. And if I want to see that, I can do disassemble, exit. That's all right. And now, this is even shorter. This is one of those C library routines I was talking about. This is going to call something else called run exit handlers. This may seem ridiculous, but this is how things are. You call one routine, it calls another, it calls another. They're all there for reasons having to do with being compatible with many codes. So let's disassemble this one. And this one is long and does a bunch of tests and jumps into other code. And that's all this junk, but it's eventually going to prepare for the syscall, which is at the label __ exit. And it's in here someplace. But anyway, I'm not going to hunt for it right now, so I'm proceed. These are all precursors to the actual routine, which is this one. Disassemble. Oops. Whoa, whoa. Okay. This one. Okay, disassemble. __ exit. There. Or is it 1_ just a moment? It's 1_ exit is the routine that's finally going to do it. This is the one that finally does int 80. So this is something you get used to. If you use C, it's going to call several routines doing housekeeping chores that are sort of irritating, and then finally do a syscall. This is why if you wrote it in C and compiled it, as you saw, it would be 300 kilobytes big to do an exit, when you can actually do this in like 6 bytes of assembly language. That's why you write your own shellcode, and it is super small. And if you go through all the burden of a C compiler, it puts all this unnecessary extra stuff on it that you don't need. So, all right. So this is what really does it. And you can see All I wanted to see there was that that will eventually call exit. By the way, it does 2 syscalls. When I did it before, which I see here now. First it calls FC. Okay, so take a look at what it does. It puts 4 somewhere on the stack, 4 bytes up the stack past ESP. It puts EBX, the base pointer. Then it puts FC in EAX, and then it calls this function. So you might want to know what that function is. Let's take a look at that. Disassemble that. That function just does index80. Now, I don't know why they didn't just put index80 right there. But you know, it's a very complicated job to write a compiler, and it's got many other considerations. So this is also index80. So it calls a syscall of FC, which is 252. Syscall 252 is not exit, it's exit thread, exit group that kills all threads. Then it calls exit. So this part here is the only part that we really need to exit our single-threaded C program. The rest is for more complicated situations which we are not using. So that's what's happening here. So now we're going to write shellcode for the exit syscall. So the plan is to make simple, compact shellcode. And like I say, there will be no error handling. So if anything goes wrong, it will just crash because we're trying to make it small. And so here is one way to do it. This is the 7 instructions that the final routine of the C compiler did. It moved, put EBX on the stack, then it put FC on the stack and called index80. Then it put 1 on the stack and called index80 again. That's one way to do it, but we don't really need to call exit group. It'd be good enough to just call exit. So if you want to know about these syscalls, you can find them online. I put a link to chapter 3M here. If you go there, here's a Linux syscall reference, and it will show you how to use them. So here are the first few syscalls, and we're going to use the first one, sysexit. So EAX has to be 1, EBX is the error code. Remember, we did exit parentheses 0. That's the number you send to the calling program saying I exited. And by convention in C programming and Unix, when you return 0, that means everything's okay. If you return a number other than 0, that means something went wrong, and the number that comes back is the error code. So that's all. 1 means it's exit, and this is the error code we return. That's all we have to do, and then call sysexit. And if you click on this, you can see the actual kernel code, and this is where Linus Torvald lives. This is why when they made the patches for Spectre, he was screaming and yelling that you did it wrong, because his whole life is this thing, the Linux kernel. This is what he wrote, and he's now the maintainer of the Linux kernel, and every change to it has to be approved by him. It's the product of one mind. It always has been. Many people contribute, and he is the final judge, and he is famously very, very harsh about it, constantly screaming abusively at anyone who dares to do the wrong thing in the kernel. And there's an elite bunch of people out there that can write code good enough to go right in the kernel, and they are much, much, much more knowledgeable than an average developer that just writes ordinary software. They have to write really the best software to go in the kernel because everything else depends on that code. Anyway, so that's the specifications for this function we're about to use. And so here's the assembly code that will do it. Now, before we wrote C code and compiled it with GCC, which is the high-level language, but you can write assembly code directly. And that's what it looks like. So let me bring it up in my SSH section here. I'll get out of this one. And it's exit.asm. So here it is. So this, you define, it has only one section, a text section. Remember, a text section is the part that contains the code. You define a variable called start, which tells it where to start. This defines it as a global variable, and this tells you where it is. This is the equivalent of main, where to start. Then it executes 3 instructions. Put a 0 in EBX, put a 1 in EAX, and call int80. That will accomplish exit parentheses 0 and parentheses. The 0 will be returned to the calling routine. That's it. So to compile that, you don't use GCC because it's not C, you use NASM. NASM is the assembler. So NASM creates an object file from an assembly language file. So you do it with NASM minus f-elf. This tells it what format it is. Elf is executable linking format. That is Linux format. And you give it the source code, which is exit.asm. That creates exit.o. This is called object code, and that's what was just created on my system. Yeah, exit.o. What's that? Number 3. Oh, this one here. Right. Thank you. That's it. Good. Now I feel better. Good. Exit. No. Thank you. So now all right. And now to link it is a separate step. You have to link it with LD, which is the linker. You cannot run it until you have linked. The object code is like a library. It's code, but it's portable. It hasn't yet been connected to something that can launch it from the operating system. You have to link files together to make something that will run. And you do that with LD -O. And I'll call the thing exit shellcode and feed it exit.o. Ordinarily, you have to link several things together, like your source code, your custom library, the system libraries, they all have to be linked together. This is very simple. So now I've created something called exit shellcode. And if I look at it, oh, thank you. I did not see it. Let's see what's in the chat. Good. Does it matter in what order you do, move EBX and move EA1? It does not, as long as you move them both. Before you call int 80, you have to have the right contents in the registers. They could get there in any order. When you call it, it will look in the registers for those values, and they have to be there. But it doesn't matter what order you do it in. Good. Thank you for telling me. So now I get exit shellcode. So if I run it, again, it just returns without crashing. It's done at exit, which is not very exciting, but it runs. But the interesting thing is to see what's inside there. Now, we could open it in GDB and do disassemble, but another way to do it, which you should learn about, is objdump. Objdump is very handy. It can do quite a few things, but the simplest thing it can do is disassemble code. So you feed it any kind of executable file, and it will disassemble it all and just print it on the screen. Normally, this makes page after page of data, so I feed it into a text file and a text editor like Nano to hunt through it. But this file is so simple, of course, there's almost nothing to it. That is the entire assembled code. It is 3 assembly language commands. And those 3 assembly language commands turn into 12 bytes of raw binary machine language. This is what loads 0 into EBX. Now, the reason it does, the BB is move into EBX. 1 byte to specify that. Then it's a 32-bit processor, so it has to move 32 bits of data, so it takes 4 bytes to write it down. So this is 0, 4 bytes of 0. This is 1, in little endian order, as you're probably getting used to. The 1 is here, and these are the high-order bytes. They're all 0. The B8 moves into EX. The BB moves into EBX, and now this is the int CD, and there's the number. That's it. So those 12 bytes of code will perform an exit. Okay, or you could compile it with GCC and have 347 kilobytes of code to do the same thing. Yeah.
Right, earlier you LS, all the things sort of exit, all the files.
Yeah.
Now you won't see that if you do this, right?
Well, that was just, I made many of them. And the files I have here are just from various demonstrations.
But I mean, if you do what you just did,
objdump?
Small with 8 bytes. You won't see
Yes, you mean when I went to GDB, we went through all these preliminary steps. Is that what you're talking about?
No, I mean like when the final malware is finally embedded in the kernel.
Yeah.
And they used to have something that's anti-malware. If there's no, even if there's no access exception, then will the malware detector be able to see all these files with different names? It seems strange.
Well, these shellcodes don't even have them as files or names. You're going to be inserting them into running processes. The files, all the files with file names are just what we use to develop it. When you actually use it, you typically don't have any file involved at all. You just put it in like a password or something and send it to the server and it's executed on the server. All the files are just for us. They're not part of the actual exploit. I hope that helps.
Yes.
Okay, so that's the game. So now, one thing you often do when you're developing your own shellcode, you have to test it. And there are various ways to do it. Here's the one that I thought worked better. The one in the textbook didn't work as well as it should, so I found this one online, testexit.c. Because now this, again, may seem like we're going around in circles, but if you create shellcode, you have to test it to make sure it works. especially when you start modifying it in the binary. And so it's useful to have C code that will run your shellcode just so you can see if it works. So here's the shellcode in raw binary, in hexadecimal. And now what this crazy stuff does is define a C function and then define a variable that points to some code. And then set that to point to the address of this array. And this is the fundamental thing I mentioned in the first lecture. The fundamental reason why all of our attacks are going to work is because computers do not know what they're doing. It's all just bits. And they cannot tell code from images, from text. It's all just bits. So we're going to load a string variable with what ought to be text, and then we're going to jump to it like it was executable code, and the computer will just do it because it's all the same to the computer. It doesn't make any sense. A higher level language would not let you do it, but as far as the processor is concerned, bytes are bytes, and you can use it for anything you want. It would probably be great if somebody invented a computer where there was a extra couple of bits in every byte that specify what this byte is for. So text bytes were different than code bytes, but that thing does not exist. That's not what we're using. We're using this crazy system. So these things, which are intended to be just characters, can be run like they were code with this kind of thing. You're just going to jump to it and execute that string array as if it was a function, and it will work. This is the kind of madness that C lets you do that other languages like Visual Basic would never let you do because it's insane. But it's because C is a very thin shell on top of assembler. You're controlling the thing bit by bit. You can do anything. And you can do crazy things, and it never argues with you. Yeah.
So this program with assembly code only works for the processor?
Yes. This would only work for the Intel. If you had an ARM processor, you'd have to have different bytes here. You'd have to go get ARM assembly code, make ARM machine code, and put it there. Yes, this is tied to assembly and probably only 32-bit assembly too. That's why in this class, more than any of my others, you must have 32-bit Linux. If you have 64-bit Linux, the project will not work. We'll get there in lecture 7, but the 64-bit is all different. And like this, these instructions would not run on 64-bit Linux. It can, but it doesn't by default. And in fact, on if a default, this is a huge issue. Windows is backward compatible. If you install 64-bit Windows, you can run 32-bit code on it. Microsoft always supports one generation back. If you have 32-bit Windows, you can run 16-bit code on it. But Linux does not do that. If you have a 64-bit OS and you try to run 32-bit code, it will not run. And it will not even tell you what the problem is. It will tell you, I don't have enough permission to run this file, which will start you down the wrong path of trying to be root or something, because they don't bother to give you the libraries to handle 32-bit code by default. You can add them, but they're not there by default. So it's cruel. In a Windows system, it would work better, yes. And when we get to Windows exploits, you don't have to worry so much. That's why it's perfectly fine that we only do 32-bit Windows exploits, because they'll run in 64-bit systems. But in Linux, you have to separately develop 32 and 64-bit exploits. Because the whole point of Linux is you are supposed to be an expert. You're supposed to understand what you're doing. You're not supposed to be running a bunch of crap that you don't even understand that somebody else wrote before. So you are expected to understand. I'm in a 64-bit system. I have to recompile everything for 64. That is expected. Whereas in Windows, it's the opposite. You're running a business. You're just part of a corporate chain. There's a whole bunch of legacy software that is not your problem, and you just want it to work. And Microsoft is there because they understand you're here to make money, whereas in Linux, people, you're expected to really understand your servers better. So they think nothing of decisions like this that make it hard to use, like making you use the command line all the time. That's just expected in Linux. Windows people don't want to learn the command line, and they don't care. They're trying to make money. They're executives. People write nice GUIs for everything. In Linux, nobody cares because they say, if you can't use the command line, just get lost. We can't deal with you bums. Go use Windows. Anyway, so that's the assembly code that's the C code. So you can compile that. And when, Chow, thank you. I don't know how you're seeing them. I don't see them. All right. So link 3K points to backtrack. Yeah, Kali should definitely work better. They don't use backtrack. Backtrack is over. Use Kali. And I'm using the latest Kali also in my examples. Kali, yeah, I'm sorry about that. If I have a link to backtrack, it's probably not even available anymore. Forget backtrack. Backtrack is over. Oh, no, they changed the code. In fact, backtrack went through versions that were based on Slack and stuff. It's really quite a different product. But backtrack was the long ago precursor to Kali. Yeah, good. These are important questions. Yeah. College what?
The latest Kali.
Yeah, the latest Kali is fine. Older ones, they did. So that's why I use SSH. Another student, by the way, has another workaround he told me. He just opens the browser inside Kali and gets the instructions inside Kali. So you cut and paste inside there. That'll work.
But if you go SSH, don't you need to run the SSH server?
You do. You do. So this is important for anybody that didn't get it last time. If you are trying to use modern versions of Kali, go to the page for this class and go to projects, and right here are the fixes. This is super important. If you're trying to do the projects on a modern version of Kali, you will be very frustrated unless you do this stuff. Every version of Kali breaks a bunch of stuff, and this time they broke VMware tools, which is very annoying. Before you do anything, do this to your Kali, or you will suffer. Because without cut and paste, it's no fun. This is the most important part. Install and run SSH server, and then you'll have a window you can cut and paste into. So be aware of that. And here's another chat coming in, I see. All right. If you use open VM tools, you can copy and paste. Okay, I can try it. I tried it before and I couldn't get it to work, but someone else says he got it working. Anyway, I'll try it again then. But anyway, SSH is a successful workaround. So I wanted to compile my test exit. Well, I'm not going to bother. If you compile it, it will of course run. I needed the Z exec stack option for this. What happens is each version of GCC turns on more and more security features, and you have to turn them off to do these goofy tricks. So now, here, let me compile it just to make sure I'm right on track here. Let's go here. Okay, so it's GCC, putting the output in test exit, and taking the input from test exit.c, and allowing the stack to run executable code, which is no longer permitted by default. That's the plan. And so, I have in the underscore here for my input file. There, that did it. So now if I do ls-l exec star or test, okay. Okay, here's the file I just created called test exit, 7,000 bytes long. And if I run it, it exits. All of this is pretty unexciting accomplishments, but now we're going to see how it works. If you want to see all the functions that were called to do this, you can use strace. This is stack trace, and you run it on test exit, and you get a lot of output. This shows you all the various things it called. It called this file, and this file had these protections on it: protected read, protected write, and so on, but it eventually ended calling exit 0. So this stuff would be useful if I wanted to get into all the things C did to launch it, but I don't really care. It did a whole bunch of extra garbage for C, and then it did the exit 0. This is all I cared. The end result is it accomplished an exit 0. So all I wanted to do was to test my shellcode, and it does do that after a whole bunch of extra work that C does to handle more complicated situations that don't matter to me right now. So that's the game there. So now we got to make injectable shellcode. We have now made shellcode that exits, which is pretty boring, but at least it's shellcode of a sort. But the problem is this is useless because remember, you can't use bad characters, and 0 is almost always a bad character because it terminates C strings. So any program you're exploiting that was written in C will not keep reading past a 0. So this 0, 0, 0, 0 will never get in there, just the first 0, and then it will interpret it as the end of the string and none of the rest of the code will get there. So we have to get rid of all those nulls. So to get rid of nulls, we have to find instructions that aren't all full of zeros. So instead of moving an immediate value of 0 into a register, which would give me 4 bytes full of 0, I do XOR EBX with EBX. That will flip the bits wherever there's a 1 in both of the arguments. And since I put the same argument in twice, it'll take every bit that is currently 1 and flip it to 0. And all the bits that are 0, it won't flip and leave them at 0. So this will end up putting a 0 in EBX, but it doesn't involve literally entering a 0, which would break my shellcode. Yeah?
Do you mind writing down what you said on the whiteboard how the XOR works?
Yeah, I'll type it here so people can see it remotely if anybody else has the same issue. That's fine. Okay, so the way XOR works is, if I have a 1 XOR 1, I get 0. If I have 0 XOR 1, I get 1. And if I have 0 XOR 0, I get 0. That's how the single bits work. It's the exclusive OR. It's 1 if the 2 bits are different. If the 2 bits are the same, the answer is 0. So now, suppose, let me make this nice and big, right? Suppose EBX contains some value, like 00111100. Then if I have another copy of EBX, and I XOR it, I'll do it here. Okay, then let's put it here. Okay, so what happens is 0 XOR 0 is 0. 1 XOR 1 is also 0. You get all zeros. Okay, because of course, the only way you can get 1 is if the 2 inputs are different. And if I XOR anything with itself, it's not different, so I get 0. This is a mathematical operation which seems like a very convoluted way to achieve the answer 0 to us, but it works in the processor. This is like if you have like people that want to talk about selling drugs online or in chat or in the telephone, they don't want to do it. They make up fake words, euphemisms for what they're referring. You want to talk about something without referring to it directly. We want to put a 0 in there, but we don't want to mention the name 0 because that'll break everything. We have to indirectly achieve 0 without talking about the forbidden thing. So this is how you can create a 0 without directly referencing 0. And that's the trick you do for shellcode. So if, here's another one, move EAX1. Remember, we wanted to return a 1. Well, we can't refer to a 1 literally either because a 1 has 3 bytes of 0 at the high bytes. So we have to do it some other way. There are various tricks, but this is the simple one, which is to go all the way back to 8-bit commands. The modern 32-bit processor does have some commands that refer to only 8 bits at a time. So this will move 1 into the lowest 8 bits of the 32A register. One thing that I've always kind of wondered about is technically, I believe, if you had something else other than zeros in the other 24 bits, it would remain there. So you might not end up with 0, but in practice, it doesn't seem to happen. So it might be fun to play with that and see if it actually affects the other bytes. But anyway, this way, so if you do that, here's what happens. The old instruction was move EBX0. The new instruction is XOR EBX with EBX. The old instruction is move AX1. The new one is move AL1, which moves only 8 bits. And this is not 0, it's 1. And now you have int 80. So you can compile the new one, and you'll see how different it is. Let me do it live here. It's exit 2. So if I nano exit 2, .asm, you see here it is. It does the XOR instead of the 0, and it moves AL instead of EAX. So it moves only 8 bits. And so if I compile this one, up here I had my LD, that's the loader, and there's the NASM. So if I exit 2, and now ls minus L exit 2 star, I've now created exit 2.0, and if I load that, which is up here someplace, there's my loader. So let's call that exit 2 shellcode and load it from exit 2.0 to make the executable file. And now if I look at how big that is now 540 bytes big. And if I want to see the assembly code, I can use objdump minus D on exit 2 shellcode. And now take a look at the difference. It is now 6 bytes long instead of 12 because these commands are much shorter. So XOR EBX with EBX is just 31 dB. It doesn't refer to any zeros. To put 1 in AL, it puts 1 in AL with the B0 command. There's no zeros, and the int 80 is the same. So not only is my shellcode shorter, but it also no longer contains any zeros. So it's more useful. So that's what you do. Now what MSF payload does, it can remove any characters by encoding it, and it will add a little decoder to the front, like a self-unzipping executable. But anyway, this is the simple way to clean up your shellcode. You have to use special languages. This is, you have to carefully choose commands that will not compile into zeros. And that's the game. So now, Now we have to face the other irritating problem, which is all this shellcode has accomplished absolutely nothing except exiting. So this is, of course, not what we want. What you'd like to do is something like open a listening port or a remote TCP connection of some kind. So this is just a DOS command. If you were to inject this code and run it, the program would stop and exit. So that's a polite denial of service command, but that's not really of any value. So here's what we'd like to do. To make shellcode, you write high-level code in, say, C, you compile and disassemble. Then you analyze the assembly to see how the C compiler did it. Then you clean it up to remove the extra function calls you don't need and to get rid of the zeros it put in. And then you make your own shell command. This is typically how you do it. Now, if you were a master assembly language programmer, you could just write shellcode directly. But in practice, this is mostly what people do. Let the compiler do it and then clean up the mess it creates to get there. And this is what other people have done for us that wrote MSF payload. MSF Venom, pardon me. MSF payload was the old name. MSF Venom is the new name. So if you want, now you have to create a new process in Linux. And there are two ways to do it: fork and exec-ve. Exec-ve will create a new process and replace the existing process with the new one. Fork will copy a process, so there are now two processes running. Then use fork and exec-ve together. We're going to use the simpler one, just exec-ve. So here is, now exec-ve will execute a command, and you put the command here as a literal shell command, /bin/sh, and then the next command, the next argument is, I think, arguments to it, which there aren't any, so we put it in a null. And you just call exec-ve here. So let's play with this one. And that's nano exec-ve.c. So here it is. I just define an array called happy that has enough, 2 string values can go in there. The first one is bin.sh. Now, by the way, before I do this, let me remind you, bin.sh, this is a bash shell. There are different shells in Linux. They live in the bin directory. If you do bin.sh, you get a different prompt. It doesn't print the name of your identity and the name of the directory, and it just prints this. This is called, I think, a C shell or a corn shell or something. Linux experts will know. This is a corn, okay. So if you exit this, you're now back to bash. What's that? /bin/sh. Let's do ls-l/bin pipe more. Here's most of your Linux commands are here. And bash is one shell and sh is another shell. If you execute shell commands in a script, you typically run them in sh, not in bash, because bash is actually intended for interactive use by humans and it has a lot of extra overhead, like your history file. So it's, that's why there's different shells in Linux. There's another one called dash and so on. Anyway, so that's one way. This is a very simple shell code here that's going to open a second shell prompt. So that's what that command does. And this exec-ve will just execute that command. Here's the command. There's the remaining arguments, of which there are none, that I just call exec-ve. This is how I use a C routine to call the correct kernel routine to do that. So I compile it. Here comes some comments. Echo shell will tell you the active shell, yes. And echo $shell. So let me do that actually. That's a good thing to show you. So echo $shell tells me that I'm in bash. And if I do bin./sh and now do that again, now it's still telling me I'm in bin bash, so something did go wrong there. I'm afraid these environment variables aren't updated by these other ones. So
that's correct.
This is not bash anymore, though. This is now dash or something.
No, that's bash.
This is bash?
Yes, the same thing. I just looked it
Oh,
up.
bin.sh is bash?
I agree with you, and I want to verify. And I looked it up. Since we have bash and sh are they're 2 different shells with the same.
Oh,
bash,
how rude. Okay, it used to be.
one is symbolic thing, though.
One is what?
Symbolic thing.
Ah.
It's like extra features. Like
Oh, okay.
When you wrote bash, I think it executes bash RC or bash profile, which those are variables. But when you do bash sh, I think it bypasses all your extra stuff and just goes directly to shell. Bash shell.
And dash is also bash. How rude. Okay, there used to be a bunch of different ones. It seems like Kali, they're all just bash now. I bet if I had a bunch, I'd get a different answer there. Anyway, for most purposes, they're all the same. These are good points. Let's see what he says here. Many modern Linuxes have bin.sh, yes, symlink to bash. Executing bin.sh won't parse your environment to change your shell. Okay, fair enough. Thank you. Good. I appreciate it. You guys are more knowledgeable about Linux than me, and I appreciate the help. If you have any good comments, chime in. Don't be shy. Like if I'm wrong, especially chime in, because my ego is less important than the accuracy of the information. So, all right. Let me see if I can move this junk out of the way. I think it doesn't project, but I've got the chat room in my way. All right. So, good. So here is the main. Right, and it looks like I disassembled it in GDB. So let's compile this mess. Let me make my window a little smaller so I can see. Okay, so we're going to compile this mess, cat exec ve.c. There it is. So to compile it is gcc static, because I want all the libraries included instead of going off somewhere else. And then exec ve, and the source code comes from exec. I thank you, -o, good. And it's exec.ve.c. Okay, now I'm going to do ls-l like I've been doing. So there is the executable file I just created, 637 kilobytes of glorious code. And the only thing I care about is main, so I'm going to run it in GDB. Well, first let's run it, exec ve. It does work, it creates that other shell. So I can exit from that shell and get back to this one. And now I can debug it. Okay, and now I can disassemble main. Okay, and let me make this a little smaller because there's a thing in my way here. Okay, so I'm looking for the call to exec ve, which is here. So what happens here is it pushes a 0 onto the stack, then it loads an address which is 10 bytes past the EBP and puts it in ECX, or it puts ECX on there. Then it pushes that on the stack. So that's an address that points to an object on the stack, which is going to be the string variable that contains /bin/sh. Then it pushes these things on a stack and calls exec.ve. So these are the parameters being sent to exec.ve. Now, exec.ve takes 3 arguments, and you'll find them if you go to the man page for exec.ve. And they are a file name pointer, then a pointer to an argument list, and a pointer to environment variables, which could be used when you execute it so you know who you are and such, which can just be null for our purposes. So here's what you do. First, you have a pointer to a string containing the code to execute, /bin/sh, then a pointer to the argument array, including that one you just had, which we're calling happy in our C source code, and then a pointer to the environment array. We're just using null for that. We're running this without any environment variables. And so if I do an obj dump of exec.ve, I will see how it puts those in there. It pushes EBX to get ready to return from this. Here it puts up 10 past the stack pointer is the pointer to the array, to the command /bin/sh. Then it puts this stuff in ECX and in EBX, and it puts a B in EAX and then calls int 80 because it is syscall 12 is exec.ve and B is 11. Syscall 11, pardon me, B is 11. So that's the game there. And this is the final assembly code that will be translated into shellcode. You define a, and in the book, they go into a lot of detail. See, now that you've done it, you compile it, and then you go clean it up. And I've skipped over this because I just want you to get the general idea. In the book, they now get rid of all the nulls and such. And they create assembly code that minimally accomplishes that exec.ve. That's as far as I wanted to take you on that stuff today, because we got other fish to fry. And I'm not really going to push the assembly code any more than that next course, because there's a whole course in it, and you pretty much would have to take that to get into the details of it. But you should understand what's going on. So I have some Kahoots about this, and then I want to demonstrate 2 projects where we'll just go through the whole process so you've seen it. So let's start with these here Kahoots, and we're right at the end of the first hour. This is fine because I wanted to make the project demonstrations into a separate video so people can refer to that easily when they're doing the projects. So let's just do these Kahoots, and then we'll take a 10-minute break, and I will demonstrate some projects. So the Kahoots are here. And this must be chapter 3 in It's my Kahoot. And it's going to be chapter 3 right there. Great. Okay. And classic will be fine. And you need some sound. Okay. Wow, 24 people online. Okay. Let me mute them so they don't irritate each other, although I guess it's kind of late for that. But I guess they would have told me if they were irritating each other. I appreciate your help pointing out the chat. Recently, I used Zoom to live stream something, and all the people were irritating one another with noise, and I didn't notice. So the people that streamed didn't actually get any benefit out of it. I'd like to prevent that when possible. Let me know if something is wrong.
It's okay, they're just ignoring our requests.
Well, I know, but the thing is, I wasn't even there.
No, not you.
I know, but
Messaging the
But of course, there's always somebody that logs in and then they go off to the bathroom or something and leave their dog barking and they don't know.
Well, one guy ordered a coffee, long and sweet with a glaze going on.
Yeah. That's the thing. A lot of see the thing is they have their sound turned down. They don't know the mic is on. It's an understandable mistake. It's in my opinion, it's a defect of the Kahoot software. It ought to just auto mute everybody when they join. And I even found an option like that and turned it on, but it doesn't seem to work. So it might also be my incompetence at operating the product. But anyway, let's see if anybody else wants to Kahoot. There are 24 people Zooming, so I would think more of them would want to Kahoot, but we will see. It may be that 20 of them have wandered off and they're ordering coffee and not really paying attention. And I also noticed that the numbers are declining. This is what I thought. I have like 250 people sign up for this class, but I think not that many really want to do it when they find out. This is not like 123 where you're picking a lock. This is really kind of slogging through binary and hex and assembler. Most people are going to decide this is not a fun TV show after the first episode or two. It's only fun if you're at this level, ready for this stuff. Anyway, I'll give it another 10 seconds and start it.
But this is only episode like 2 and 3.
Only what?
You can't judge the entire series off the first 3 episodes.
Well, I think you can in this case. I mean, you seriously have to not be afraid of binary and assembler, or you'll not have any fun here. That's absolutely true. And most people aren't really ready for it. All right. So, which one will turn executable code into assembly? All right, that's what Objump does. You can take an executable thing like malware and turn it into assembly easily. And it's often one of my first steps when dealing with a CTF problem or something else where I have only an executable. All right. Okay. All right, there we go. Okay, how do I get all the system calls when a program is run? Okay, that's strace. I thought it was stack trace, but maybe it's system trace. Anyway, strace is the right answer. All right, which one? So what takes you from user mode to kernel mode? That's what system calls are for. Okay, that's what they do. All right, so what will convert assembly code into object code? Okay, that's NASM, which assembles the assembly code into object code. You then have to link it to create executable code. All right, so if you have move AAX 0, what should you replace it by? that's XOR, which will do a calculation resulting in 0 without having to mention the forbidden name 0. All right. What would you do if you want to put a 1 someplace? Okay, this will put a 1 in the low 8 bits, which is what this would put it in the high 8 bits, which is not really what you want. That would result in the value 256. This is how you actually get a 1 in someplace without having to refer to any forbidden zeros. All right, so it is Bill M. Chip, I know who that is. And Chadbourne, I know who that is. And if Bill M's name actually is Bill M, I might know who that is too. All right, so I want to just demonstrate some projects, but I'm going to take a 10-minute break until 2:10 and stop this Zoom so we have a separate video to demonstrate the project. So I'll restart Zoom in 10 minutes, really about 8 minutes now. All right, we'll pick up at 2:10.